And then we'll have to go back to our PowerPoint. And we will get started from the current slide, even though we're not in this section yet. Yuck. Trying to find the slide with a lot of white space on it. I think this is my best bet here. Okay. Any questions on anything we've done so far? And I'm sorry about the strobe that we have going on here. It was about to give me a headache before. I thought, I'm about to have a migraine. But no, it was this doing it, not my eyes. So, any questions before we do example 7? Okay. If you have a book, we're on page 460, and it's chapter 7, section 7.2, the last exercise, example 7. Application of geometry. Prove that the volume of a pyramid with a square base is this, where h is the height of the pyramid and b is the area of the base. Okay, now this has nothing to do with shell method. This is just the white space that I'm using to work this problem on. Okay, so here is our drawing, and mine stinks. I'll let you know that ahead of time. That's the XY axis, X, Y. Okay. Now, I'm going to do my best to sort of do a simulated. All right, let's just imagine that's a square base on the XY axis. I mean, coming out from, perpendicular to the XY axis is what I meant to say. Because Y is going up, X is going this way. Okay? Your vertex is somewhere up here, so all 4 of these corners are going toward the vertex here. And somewhere up here along Y, we have, boy, hard to tell which line is which here. From here to here, there to there, there to there, there to there again. They're sort of a square segment here. Probably on the wrong side of it there. Oh, this is really ugly. Okay, but this thickness here is your dy here. Okay, delta y if you want to call it that. Okay. This base down here is area B. Now they don't tell you the dimensions of the base, just that it has area B. The height from here to here, this is h. Okay, the height of the pyramid. Okay. Now, what they're saying, since they didn't tell you the dimension here, we'll call this dimension little b. And of course, if a square base, this will be little b2, and this will be over here a little b. And back there it's going to be a little b. Okay? So the base is dimension b by b, giving you a total area of capital B. Okay? So capital B is equal to little b squared. All right. Now, total height is h. So the height that this is, what we need to know is the, all right, this base has dimension b. This section here, they're calling, I think, a b prime, is it? Yeah, b prime. Okay? Now, the total height is h. We need to know the area of this base here, b prime by b prime, okay? That base here, which I don't think they call it capital B prime, so I won't even confuse the issue about that. we want the area of this base in terms of y. Okay? And of course, this will be the y value of that base, somewhere right around in there. Okay? That's the y value of the base. And y is going from 0 to h. So I need to identify that somewhere here. This is your y. Okay? Variable y. Okay. Now, if you look at this from the origin here out to here, that's going to be b over 2, right? Because the total length here is b. Half of that is to the right of the axis, half to the left. So this is b over 2. Okay? This distance here is some x value that corresponds to that y. So we'll just call this x for now. But that x is actually b prime over 2, right? Because this is, again, b prime is the length of this base here. So from the y-axis to here would be b prime over 2, and you can't read that, can you? Okay. I can't either. Okay, I thought I could, but I can't. So let me see if I can clean that up a little bit. I got rid of way too much there. Okay. So this is b prime over 2. Okay, that's the x value. All right. Now, I'm going to set up a ratio here. Always a good idea. This length here is to that height there is b over 2 is to h as b prime over 2 is to this height here, and that's h minus y. Does everybody see that one? Okay. This is b over 2. This is b prime over 2. The b over 2 is the h. That triangle is similar to this triangle, which is b prime over 2 to h minus y. There's the y there. Okay. Now, that's all true. And I guess to make things a little simpler, who really cares about the over 2's? Let's just make it b. b is to h is b prime is to h minus y. Because that's true too. This length here, the whole length here, b is to h is b prime is to h over 2. So h minus y. Okay? So they make the ratio there. It is simpler, so we'll go with that one. Okay, now, they did it backwards from what I did. Of course, well, they did it sideways from what I did. They wrote the b prime over b, moving this here, moving that up top, would then be h minus y over h. It doesn't matter which way you set it up, but those are all equivalent, okay? Now, that gives you the b prime is going to give you the dimensions, the area of this, okay? Because the square of b prime is going to be the area, so that's all in terms of what was given. The h, the capital, the little b, and the y, okay? So we'll write b prime is equal to b times h minus y over h, knowing that h and b are all known. You know, with whatever pyramid that you've got there, you know those. Okay? The area of this base is b prime squared, so this is going to be b squared over h squared times h minus y squared. Right? Everybody okay with it? Okay. Now, that's the area of the base of, area of this representative square here, okay, taken out of the middle of it. So the volume is going to be the summation of all these bases, okay, from, in terms of y, the function of y, times, this times dy, b squared, b prime squared times dy is going to be the volume of that slice. So the dy is going to be there, and you're going to sum all those little volumes from 0 to h. So that's the integral. So your volume will be the integral from 0 to h. That's what y is going from 0 to h. And the b squared and the h squared can come out, b squared over h squared. And what we have there is h squared minus 2hy plus y squared dy. Okay? Buy that so far? Squaring the binomial. Okay? So let's integrate this. V is equal to b squared over h squared. And the antiderivative of h squared is h squared y. Yay? Y is the variable, h is just a constant. Agreed? Okay. Minus what? You tell me the next one. Anybody? Antiderivative of minus 2hy. Where y is your variable, h is your constant. hy squared, perfect, plus y cubed. Was there something else with it? Over 3. I thought there was. Okay. And that's going from 0 to h. Okay. Now I'll take care of the 0 part. Okay, it's done for. Okay, so you have a b squared over h squared times, and just plug in h, and you have h cubed here, minus h cubed there. My goodness, I think I can figure out what that is. That's 0. And then you have plus h cubed over 3. Okay? Well, the h squared will go into h cubed h time, and you have 1/3 b squared h, which is 1/3 that base times the height. And that's what we were asked to prove. 1/3, they put hb, I put bh. It really doesn't matter. Okay. Boy, wasn't that fun. Okay. But you see what you do here. Obvious on here, you need to do the y's. So you need to get all your function in terms of y. So basically, there's your y. Now you have to set up the ratios that are going to make that make sense, and that will be the b is a constant because you know that was given. You had to know the area of the base, so the square root of the base of that b. So that b squared is going to be in there, which is going to be this b. But that is to h as the b prime is to h minus y. Once you get that ratio there, then you can go to town. B prime is what you're looking for to get the area of this thing, because b prime squared is the area of that thing, times the dy will be the volume of that thing, and as soon as you have that, then you have it. So once you get that v prime in terms of the things you know, v and h, and your variable y, you've got it knocked pretty much. The integration is the easy part. Figuring out these relationships, that's a little bit harder. Okay. And that was all we had to do to finish 7.2. I think I assigned all these exercises, didn't I, last time? Any of the odds, either 5 or 7, they're both at Calc Chat. 5's at Calc View. 9 or 11, both at Calc Chat. 9's at Calc View. 13 or 15, both at Calc Chat. 13's at Calc View. 17 or 19, both at Calc Chat. 17's at Calc View. 21 or 23, both at Calc Chat. 23's at Calc View. Any of the odds, 25 to 31, all at Calc Chat. 33 or 35, Calc Chat. 37 or 39, Calc Chat. 37's at Calc View. Any of the odds, 41 to 47, all at Calc Chat. 49 or 51, Calc Chat. 53s and exploring concepts. If you want to take a look at that, you can. It should be at Calc Chat. 55, comparing volumes, Calc Chat. 57, Calc Chat. 59, Calc Chat. 61, Calc Chat. You don't have to do all these. Do whichever ones you, I would say maybe 59 through, they just keep on going on and on, don't they? Through 69, any of those that you feel like are challenging or things that you might be interested in, they all should be at Calc Chat. 71s, think about it, so you could think about doing that if you'd like. 72 is I don't even know how to pronounce this. Cavalieri's problem, or something like that. It's too many syllables. Italian guy, I think. Pretty interesting theorem. The only reason I pointed out is the 72 is even. You don't have to do it. But if you wanted to do that as a paper topic, who was he? How did he develop this theorem? How do we use this theorem? Who uses this? Anything such as that. That's the only reason I mentioned that. 73s or 75, both are using cross sections, so I'll let you figure that. 75 looks like a real bear to me, but I don't know. I haven't looked at it carefully. And 77 is the last one, volume of the wedge. Okay, now we're ready for 7.3, and that's where we are now. So let me clear this off the screen, and we'll back up and pick up with 17.3. So we're still in Chapter 7, Applications of Integration. This time, 7.3, we're going to do volume by the shell method. Before we did the disk method or the washer method, depending if you had a hole in the middle or not. Okay. Now we're going to do the shell method. So our objectives here are to find the volume of a solid of revolution using a shell method rather than a disk method. We'll compare the uses of disk and shell methods. Okay. So let's do the shell method. We've said it several times, and here we say it again, the shell method. An alternative method for finding the volume of solid of revolution is called the shell method because it uses cylindrical shells rather than circular disks. Okay? The comparison of the advantages of the disk and shell methods is given later in the section, so we'll wait and do that later. Consider a representative rectangle. And this is the rectangle we're talking about, this little reddish looking thing there. That's that little rectangle there. The length of that rectangle is h, and the width of that rectangle they call w, which I would call a d something. Okay, looks like right here that would be a dy perhaps, but we'll just call it h and w for now. Height, which is, they have them going crossways from what I would do h and w, but it's okay. So that's your length, that's your width. Okay? Now, we're going to revolve that little rectangle around the horizontal axis here. Okay? Now, the interior of that little rectangle, no, I'm sorry, the center of that rectangle, they're going to say, is P from the axis. So the interior is P minus W over 2, and the exterior, the longer side, is P plus W over 2. And revolving that around the axis that you're doing. W is the width of the rectangle. H is the height, even though it's lying on its side here, so it doesn't look like a height. And P is the distance between the axis of revolution and the center of the rectangle. We're going to revolve that around the axis of rotation, or revolution, I guess. Okay. When that rectangle is revolved around about the axis of revolution, it forms a cylindrical shell or a tube of thickness W. That W stays all the way around. To find the volume of that shell, consider two cylinders, the inner cylinder and the outer cylinder. And they're pretty close to each other. The radius of the large cylinder corresponds to the outer radius of the shell. That was our P plus W over 2. The radius of the smaller cylinder corresponds to the inner radius of the shell, P minus W over 2. Because P is the average radius of the shell, you know that the outer radius is this and the outer inner radius is that, like I just said. Boy, this looks like it's going to be fun. Okay, the volume of the shell is then the volume of the outer cylinder minus the volume of the hole, or the inner cylinder. So that would be pi times P plus 2 squared. Okay, that's the radius, okay, of the outer one, H. H is the same. Minus pi times P minus W over 2 squared times H. And they skip a lot of detail here, but if you squared this, you'd have P squared plus twice the product of these two, which is just PW, plus W squared over 4, okay? The pi and H are the same, they're going to be multiplied by it all. Minus, and this will be pi P squared, but this will be a minus PW, and then plus this thing, squared, okay, and H. Well, guess what? The pi P squareds, H, this subtracts from that one, and the pi, because this squared is the same as that squared, okay, they subtract away, so all you've got is the difference of the inner terms, which is a PW minus a minus PW, which is another, so that's 2PW. So it's 2 pi PWH. Why they rearrange the order so much, but it works. Okay? Which then leads to be 2 pi, that's why they brought that out, times the average radius, that's the P, times the height, times the thickness. Okay? Now, you can use that formula to find the volume of a solid of revolution. Now let's go back. If you had just said, let's just take that as the average radius, P, 2 pi P. Okay, here's what I want you to do. Take your scissors, okay? Cut anywhere, I don't care where, along that shell and flatten it out, okay? Okay? That flattens out to be a rectangle. The length of that rectangle is the circumference of that circle, 2 pi P, okay? The width of the rectangle is H, and the thickness of that is W. So 2 pi P WH, that's what you get. And it seems like to me that would have been a lot easier to go that route than to do the halves in and out, and then you see they all disappear anyway. But that's what you use. The formula for the volume of this is the length times the thickness times the radius. Okay? That's what it is. And the radius is 2 pi, I'm sorry, not the radius. The circumference, which is 2 pi times the radius. That to me is the way to do it. Okay? Notice it's 2 pi. Now if you remember before when we did this method, it was always the pi out front because it's pi r squared. This you got a circumference, so it's 2 pi times whatever is inside. So that's one little difference. This will have a 2 pi where the other had a pi. But you're multiplying different things. For instance, the plane region is revolved about a line to form the indicated solid. Okay, so here's the plane region. It's going to be a triangle here. Okay? It's revolved around this line. So the base of this triangle is going to be C units above the line, and the tip is going to be E units above. So if you can get the radius of this center of that rectangle, that's what you're going to revolve around here, okay, with that radius, in terms of y, because you see your thickness is dy, or they're calling it delta y, a little more precise, I guess. But you also need this length of this rectangle, which they were calling h, as some function of y. Because you see, once you choose a dy, you need your radius in terms of y, and you need the height in terms of y. The thickness is already in dy. Okay. Now, so this is all sort of esoteric here. We don't have any numbers, we don't have any ratios, we don't know anything about these dimensions, we just know that's what we've got. The width of this strip is your h, your radius is going to be your p, and your thickness, of course, is going to be your dy. And because you're doing these strips around here, you do the volume of each one as you go y from C to D. And that will give you what you need. Okay? Remembering that length times width times 2 pi the radius. 2 pi your p here. Okay. All those are functions of y. Consider a horizontal rectangle with delta y, then the plane region is revolved around the line parallel to the x-axis. We don't know where the axis is, but parallel to the x-axis. Then the rectangle generates a representative shell whose volume is delta v for that shell, 2 pi times the radius, that's going to be the circumference, times the height is going to be the length, and the delta y is going to be the width. So that will give it to you. So you can approximate the volume of the solid by n such shells of thickness delta y, height h of y sub I, average radius of p of y sub I. So the volume of the solid will be the summation of all those. The 2 pi can come out front, which is what they do. And then it's the summation from I equal 1 to n. P is a function of y, h is a function of y, times your delta y. Okay? That approximation appears to become better and better and better as your norm, the norm, which is the maximum thickness of your delta y's, the norm is approaching 0. That means your n, the number of slices or shells that you have is approaching infinity. So the volume will be the limit as that delta is approaching 0, the norm is approaching 0, but your n is approaching infinity. 2 pi times this thing that we just determined here. And this summation becomes an integral. The delta becomes a d, and this goes from C to D, which from our picture, that was the limits of y, starting at C, going to D. Okay. So, as normal, the formula, not that bad to remember, 2 pi times the radius, times the length, times the thickness. That's pretty simple. To me, the issue is finding that P is a function of y and H is a function of y. Once you do that, because you've already chosen the dy to be things that everybody has to be in terms of y, C and D in terms of the limits of y. So getting those two values basically is your problem. Okay? The integration is the easy part, right? Of course. Say yes. Okay, good. All right. So here's the shell method. The Find the volume of solid of revolution with the shell method. Use one of the formulas below. If you have a horizontal axis of revolution, then you want your shell to be the dy's. So your volume would be 2 pi times the interval from C to D. That's why they chose C to D. That's always the limits on y. The P of y, H of y. 2 pi P is your circumference. H is your length. Dy is the thickness. Or if you're vertical axis of revolution, then you use your dx. Okay, because you have a dx here going around. So 2 pi P of x, now you have to have that radius in terms of the x, not in terms of y. The height in terms of x as a function of x rather than a function of y. And of course they like to have x is going from A to B. So this is what you're moving around here. This rectangle you're moving around here. dx, the P is a function of x, and the height is a function of x. You need to get everything in terms of x's. Okay. Make sense so far? Okay. Now, things to note. If you flash back to your disk, if you're doing vertical disk, how do I express that? Axis of revolution, horizontal axis of revolution, then your D's are your DX's for the disk or the washers, okay? And if you're doing a vertical axis of revolution, your D's are your DY's. So you see your deltas flip between shells and disk. So whichever is the easier one to do, that's the one you go with. I wasn't supposed to say that yet, but it seemed like a good place to do it. All right, so here's example 1. Bottom of page 466 if you're following in a book. Find the volume of a solid formed by revolving the region bounded by y is equal to x minus x cubed. Now, as soon as I see this, I'm saying to myself, let's do dy's, because you already got one function as a function of x. So I said it backwards. So we want dx's. We want dx's. Okay? And the x-axis, okay? And you're doing this between x equal 1, 0, and 1. Yes, dx's look good there too, because your limits there are for x's. About the y-axis, vertical axis, yeah, it's going to be a shell. Okay? All right. So I really don't want to draw the graph, but I guess I've got to. I probably don't want to draw it here, but I'm going to. Okay. Y is equal to x minus x cubed. When x is 0, y is 0. When x is 1, y is 0. Right? And when x is, say, 0.5, that would be 0.5 minus 1/2 minus 1/8, which would be 3/8. So your y would be, okay, if this is 1, 3/8 would be somewhere about there. So it's, I don't know what shape, there's some sort of weird shape in here doing like this, okay? This is going around the y-axis, okay? So it'll wind up being sort of a shape like this on the other side. Here's your dx's. That's going to be the shell. The height of this is simply your function height, right? Nice. Your integral is going from 0 to 1, and your radius. The radius here is x. You can't get much easier than that one. The radius here is x. How far x going from 0 to 1? The radius is x. The height is your function, y, which is, let's see what they call that, h is equal to x minus x cubed, right? And then this is your dx, or delta x if you really have a power thing. So that's your shell going around here. Now I know some of you want to do disk with dy's, don't you? Oh, that would be fun, wouldn't it? because these are going to be washers, and you're going from this end of this thing to that end. You got to get this in terms of y's, not, oh boy, yeah, try to do that. Get that as a function of y. Yes, I really want to go that way. Shell's the way to go on this one. I would say the only way to go on this one. Okay? So what would be your integral? Volume is equal to? 2 pi times the integral from, say one, 0 to 1. Is that what I heard? Yes, say yes. Okay. All right, good. What? X. Then you got to have this in there, your height, which is x minus x cubed times your dx. Okay? 2 pi the radius times the height times your width. Got it? Not really that bad. Before I start integrating, I think I want to do one thing first. What would you suggest? Second? I still can't hear.
Distribute.
Distribute, absolutely. And what would that give you? Dx. I don't know if parentheses are helpful or not there. But now I think we can integrate. Don't forget your 2 pi is out there. What will this be? Three minus x to the 5th over 5. Evaluated from 0 to 1. Oh boy, I even like those limits. Yeah, okay. And what does this give us? 2 pi times 1/3 minus 1/5. I'll do the 0 part. Okay, done. What does that give you? 2 pi times, okay, fractions. So we love these, don't we? Least common denominator? 15. How many 15ths is 1/3? 5 15ths. Minus how many 15ths is 1/5? 3 15ths. And that would be something like 4 pi over 15, wouldn't it? I think. Right? I hope. Let's see what they got. 4 pi over 15. Good for them. They got it right too. Any questions? Does that make sense? All right. Of course, this one was, they really just set it up for you so nicely, you know, just perfect set, do a spike. You got it. Okay. All right, to erase? Still writing? Okay. So let's see how they proceed. Because the axis of revolution is vertical, use a vertical representative rectangle, shown here. The width, dx, indicates that x is the variable of integration, especially since you had y in the function of x. The limits were given in functions of x as in x's. Why not? Okay. Now mine wasn't too bad. I couldn't remember if this was skewed to the right or skewed to the left. Slightly to the right. And there's that section. We know that 0, 0, and 1, 0 work there, and you have a pump going up there. And this is what you're revolving around. Axis of revolution is just your x value here. Okay, so p of x is x. The height is x minus x cubed, and the thickness is, they call it delta x. I call it dx. And so your volume would be 2 pi times the integral from a to b, which we know that what that is, your p of x, h of x, dx. And 2 pi times the integral from 0 to 1, x times x minus x cubed, dx. And that'd be 2 pi times, yeah, I want to put the minus in front. That's good. Minus x is, I don't know why they did that, plus x squared dx. When you integrate that, minus, oh boy, x to the fifth over 2 pi times minus x to the fifth over 5 plus x cubed over 3. It makes it so much easier to calculate, doesn't it? 2 pi times minus 1/5 plus 1/3, which is 4 pi over 15. Good deal. Any question? I don't know why they decided to reverse that and put minus in front. I never like minuses in front, but it's fine. Okay, that's example 1. They're skipping example 2, so let's back up and us do example 2. Find the volume of the solid formed by revolving the region bounded by the graph of x is equal to e to the minus y squared. Oh, what a good looking thing here. And the y-axis, and we're going to go from 0 to 1 on y. Okay, about the x-axis, so revolving around the x-axis. Now, just looking at the first 2 pieces of information given, what would you say you want your d to be? dy for sure. And since you're doing dy, and they give you this in terms of y, this will be revolved around the x-axis. That makes perfect sense for a shell method. Okay, so what is going to be this, by the way, is going to be your h of y, because that is indeed, I'm going to cheat and look at their graph because I don't want to graph it myself. Your y is going from 0 to 1, and they have graphed it here. And when, by the way, when y is equal to 0, what is your x? Y is equal to 0, what's your x? 1, okay. So this will be 1 here. They don't tell you that, but it is. Okay. And you're only going from 0, so you're going to terminate it here. Okay. And I don't really want to do this, but it's doing something like that. Now, if you want to know what it really is similar to, not exactly the same thing, but when you see e to the minus something squared, okay, picture this, and that's almost your bell curve thing. See, that's going to go infinitely in y, but it's going to get so close to the y-axis, because you see this thing right here, y can take on all real values from minus infinity to positive infinity, and your x is always going to be positive, so it's never going to touch the y-axis. And this is basically going to be like a bell curve. It's not going to be the bell curve because it's not normalized to be a volume of 1, but that's what it is. It's one of those statistical normal curves. It's not exactly normal, but it is. So that's why it terminates up here at 1, because it would have gone, if you let this go, it just keeps on trucking out here, approaching that. And it's not wavy like that. It's a nice smooth curve up there. And it would have done the same thing down here, and it just keeps heading out that way. We're not doing that. We're only doing this portion here. And we're revolving this around the x-axis. So this thing is being done around the x-axis. So I really did need the graph down here. Now that's a nice smooth bell curve type thing there. Okay, at 1. And we're doing dy's, so let's just go on and do this. And of course your h here is that, what we said there, e to the minus y squared. Your radius of the circle, that's just going to be y. Your P of y is equal to y. Okay? So what would be your total volume? Say again? 2 pi. Good start. Integral from 0 to 1. That means your dy is going to be out here somewhere. Y times e to the minus y squared dy. So I didn't need to write dy way out there. I should have looked ahead. Thank goodness they gave us this weird, almost bell curve-like thing, because this is going to be here. How can we do that integral? Oh, man.
Isn't like e to the negative y squared with that still just be e to the negative y squared?
Say that one more time.
Oh, I think I'm getting it mixed up with derivative. Never mind.
Okay. What method would you use? About the only one we've had so far. We're getting the techniques in the next chapter. And you probably did this at the end of your Cal 1.
Chain rule?
Say again?
Chain rule?
It's undoing the chain rule in a sense. And what method do we use in integration that does that? Substitution method. Y'all remember that? Did y'all have it?
So like u substitution.
Okay.
Well, we substitute u.
What's that?
We use u in our substitution.
Yes, exactly.
Yeah.
Yeah, U substitution. Okay, you can call it all sorts of things. Yeah. Now, what do you choose as your U?
Y squared.
Exactly. The innermost part of your more complicated part of your solution, of your integral here, and the more complicated part is e to the y squared minus y squared, and the innermost part of that would be this. I would even go so far as to say minus y squared. The y squared probably would be a better choice, but either one will work. You just have to carry it through. So which you want to use? Did you say y squared? Okay, we'll do it that way. So let u, is this how you did it? Equal to y squared. Always the next line was then, and what was the next thing you did? A little out of du is equal to, yeah, okay, I thought that's what you said, okay. Is what?
I'm trying to remember.
2y dy, perfect, okay. Now, only problem is you don't have a 2y dy, you just have y dy. So what I wanted is a y dy, so let's divide both sides of this by 2. I don't know if y'all did it this way, but this is how I've grown to like it. So now we've got what y dy is. So let's go back up here and do your v is equal to 2 pi. That's 2 pi, that's just a constant that's out there. Going to leave off the units or the limits here for a minute, okay? And what we have, because we have this y dy, that's going to be du over 2. There's going to wind up with a du here. The over 2, let's bring out here, so that's going to wipe out the 2 there. Sleight of hand, right? Shell game. The shell game? Never mind. Shell method. Okay, never mind. Okay. Now, what do we have then? The y dy over 2 was your du. We got that. And this is e to the minus u. Because y'all did it that way, we'll have a minus u there. Now, we're everything fine except we haven't done our limits. You see, these are limits for y. We want limits for u. Well, this thing right here will tell us. When y is equal to 0, what is your u? 0, so that goes in as a 0. And when y was equal to 1, what is your u? 1. Oh, wow. Don't worry, folks. They're not always going to be this way. Most of the time, that will be changing. In this case, it just happened not to. Now, we're ready to do our integration. We got pi now because we lost the 2's there. I don't know what we did with them, but we lost them somewhere. What is the antiderivative of e to the minus u?
Isn't it the same thing?
Close. It will be a e to the minus u, but now you unchain rule it. You have to have a minus. Right? Now, how do I know that? Because when I take the derivative of this, I need to get that. So the derivative of this would be minus e to the minus u times the derivative of this. This is a chain rule going this way, times the minus 1, so the minus 1 cancels out. Yeah. You got to have that minus in there. And we're going to go this from 0 to 1. Okay? So plugging in the 1 first, you get pi. Well, let's just leave the pi outside. And when you plug in a 1, what do you get? Now remember my theory about minus signs. They're there to trip you up. That's the whole purpose of having minus signs, to mess you up. So be very careful with them. Okay? That minus goes there, and you have e to the minus 1, right? There's your first term. Minus a minus, which is a plus, e to the minus 0. What's e to the minus 0? 1. Okay? So this is going to be pi times, I'm going to reverse those, 1 minus 1 over e. Is that okay? Okay. And if you wanted to fiddle with it a little bit, you could say it's pi times e minus 1 over e. Not that that's any better, but I don't know. Either of those answers is perfectly fine. Except those are all numbers there. They're not really functions anymore. If you got your calculator, I don't know which one's easier. I would think this one would be a little easier to calculate. Pi times 1 minus 1 over e would be approximately what? Anyone got it? And that, by the way, is what the book got, except they put parentheses here rather than brackets. That's fine. Anyone got it? Okay, the book got 1.986. Is that okay?
Yeah.
Okay, about 1.986. Now, this obviously is a bell curve because the area under a bell curve, the entire curve is going to be 1. Lies to 1. So you have a coefficient in front of it. So this would have had some other weird kind of things in front, including some 2 pi's or whatever, divided by pi's and stuff. But anyway, for our problem, that's the value. Almost 2. Yes?
You said for the u substitution you could have included the negative y squared.
Okay, yeah, you could have done that. Let u equal negative y squared. Then your du would have been minus 2y dy. So your y dy would be a minus 1/2. So then, yeah, and then at that point when you plug this in, you'd have a, I believe, a 0 and a minus 1, then you flip them and then you lose the minus and it turns out being exactly the same. Yeah. I think this way is probably a little bit easier. You just have to keep up your minus signs here. The other way, you have all sorts of minus signs. Keep track of them because they're only there to trip you up. It's the only reason minus signs exist, to make you make mistakes, right? Okay. Sort of. Okay. All right. Make sense? Okay. So that was example 2, and we got pretty much what they did. So let's move on to, unless there are questions. Any questions? Comparison of the disk and shell methods. Okay. The disk and the shell method can be distinguished as follows. For the disk method, the representative rectangle is always perpendicular to the axis of revolution, and the shell method is always parallel to the axis of revolution. Okay? So with this, okay, what are they doing here? Yeah, this is the disk method, revolving around the y-axis, so your representative rectangle is perpendicular to the y-axis. So it's going around this way, so this will be a washer, not a disk. The length here will be in terms of x. No, the length you have to get it in terms of y. Okay, so these r's need to be as functions of y, because your thickness here is of y, because you're going around the y-axis. So all this is going to play, and then you just integrate this from C to D. This part down here you don't even mess with, because this part in here is the part you have to subtract out. So these two r's here you have to have in terms of your variable here, which is your y. So you're going to C to D. Now, horizontal axis of revolution, your strip here for the disk method, if you're doing dy here, then, dx here, across here, that's going to make your washers again, because you're up off the x-axis here. So your height here, both of these r's need to be in terms of x's, not in terms of y. Here they need to be in terms of y, but they need to be in terms of x's. Okay? And remember, out front for the disk method is pi r squared, or r squared minus r squared here, times your thickness. So that's simply your volume formula, area times volume. The area times thickness is your volume. So that all pans out nicely. For the shell method, here's your axis of revolution, there's your rectangle, that's going around here, so that's going to be a 2 pi r, 2 pr, where p is the 2 pi p, okay, where p is the radius of revolution. And the height needs to be in terms of x's, and the p is in terms of x's. But, almost, especially if it's around the y-axis, that's just going to be x. Okay, that's the beauty of it. If your axis was over here somewhere, or over here somewhere, then you have some more finagling to do, but it's still a pretty easy process. Okay, but it's 2 pi times the radius of revolution. 2 pi times the radius is the circumference times the height times the thickness. So that gets you your volume here. Here it's pi times the r squared. So here it's the difference of the r squared, because you've got the washer, the outer minus the inner, times the dx. What's that? Thickness of your shell. Thickness of the washer. This is the thickness of the shell going around this. So we can beat that horse as much as you want to. Any questions on it? Okay. Now, what does it come down to then? Okay? Is this something you can get as a function of y easily? Because that length is going to be important here. If it's not, then do the shell method, the disk method, both of these are dy's. If you can get these radii in terms of y easily, do this. If you can't, do disk, and then do your dx's here. If you can get this easily in terms of y, do shell. If you can't, yeah. So the thing is, can you get these in terms of that? Can you get the circumference in terms of the y, especially the height in terms of the y? Here is the radii in terms of the x's, or the radii in terms of y. If you can, go with the method that fits. If they're equal, choose whichever one you want. Okay. Hope we'll see that in the next problem. Find the volume of a solid formed by revolving the region bounded by the graphs of. When I see this, I immediately want to have what? What d's? dx's, of course, okay? But let's see if it's going to make sense to do that, okay? So we're revolving around the y-axis, so I'll put my axis here, and we're going 1 here, 1 there. Probably did it a bit too. Let me bring these in a little bit. Wasn't looking ahead far enough. So, all right, I'm going to change again. Okay. So let's do 1, 2 here. We'll do 1, 1, 2 here. Okay. I don't do my spacing very well, so get over it. Okay. Now, y is equal to x squared plus 1. Okay. Here's going to be my vertex of that, and it's a parabola like that. Okay. Y is equal to 0 is going to be down here. X equals 0 is right here. And x equal 1 is right here. Okay. Okay. About the y-axis. So this is going to go around here. So I don't have this looking very parabolic. So basically this. We're going about the y-axis here. Now, since I said, you look at that and say, can we do a dx here? If we do a dx, what kind of method are we going to be using? Shell. This will be a shell because there's your dx. It's coming around the y-axis. So yeah, that looks like shell method all the way. Your height of this is going to be certainly your y. Okay, 0 to 1 x. That dx, that fits that well. Looks like picture perfect shell method to me. Okay, so what will it be? The volume will be 2 pi. Good way to start. The integral, and we're going to be doing dx as we chose, right? This is why we said dx, okay? And this also contributes to dx, okay? Looking good. So what will be the limits? 0 to 1. And then your radius, P, is going to be x. Okay, so that will be x. This is going really good. Your height here is going to be x squared plus 1, and your thickness is dx, of course. Looks like picture perfect shell method. What would you do next? Did someone say distribute? Good choice. Okay, what would that give us? X cubed plus x dx. So now we're ready to integrate 2 pi times x to the 4th over 4 plus x squared over 2, evaluated from 0 to 1. This will be 2 pi times, anyone make a guess on that? 1/4 plus 1/2. I'll do the 0 part, done. And that will be 2 pi times 3/4. And the 2 will go in the 4 twice. That would be 3 pi over 2. If my lousy figuring and writing work, 3 has pi. That should be the volume. Let's see what they got. Oh, look at that. They got it right. Okay? Now, they actually showed it doing the disc and washer method. What a pain in the neck. I mean, what a bad choice. Okay, down here, if you did this, as you're rotating this way to get your disc down here, that would be, oh, you're going across here. I want this in a different color so we don't get so confused. What color? Pick a color.
Green.
Green, you said?
Yes.
Okay, green. Okay, we'll pick that one. So if we're going to do a dy here, then for this part, that's going to be disc. Or I can just do the volume of a right circular cylinder of radius 1, height 1, pi r squared times height, so it's pi. So this part down here is pi. And then the next is going to be a washer from here to there. So this length is going to be 1 minus, and this is where it really gets nasty. You have to get this in terms of y, because you got dy's here. So you do y is equal to x squared plus 1. Subtract 1 from both sides. Y minus 1 is equal to x squared. So x is equal to the square root of y minus 1. Okay? And we don't have to do plus or minus because we're just going to do the plus side here. So let's just do that. And so it would be 1 minus this thing. And that looks like so much fun to integrate, but I'll just leave that alone. Okay. It's doable. They did it in the book. Oh, I'm sorry, I didn't quite say it right. Oh, no. Except that integral that you do with this, remember you've got a pi out front, and you've got, these are squareds. So it actually comes out much nicer than that. This part here is going from 1 to 2, because when x is 1, this goes up to 2 here. 1 to 2, your pi out front, it's 1 squared, which is 1, minus y minus 1. So this will be y. So this will be pi times the integral from 1 to 2 of minus a minus is so that will be 2 minus y dy. And that's not bad to integrate either. There's a minus sign in between the two. And I'll let you play around with that if you want to, but it's just a little extra mess. You lose your, I mean, it's just more to do. And I'm lazy. Okay. Now they say at the bottom of this, let's see, let's just see. I bet you they are going to do it, so let's watch them do it so we don't have to, okay? I'll erase all this. And they start by doing exactly this. Find the volume of solid by revolving. Did they say do it both ways? No, they just chose to do it both ways. Find the volume of a solid form, blah, 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 blah. We did this part. The washer method requires two integrals to determine the volume of the solid. The first is the one down here, and then the one up here. This is the disk method, that's the washer method. This can just be done by a shape, so that's just going to be pi. But I guess I'll carry it through completely. The outer radius is 1, the inner radius is square root of 1 minus y minus 1, like we said. That's going from 0 to 1. This is going, from 1 to 2, this is going from 0 to 1. And this really makes a lot of sense to have a little r equals 0, so we'll not fuss with that too much. And I can't believe they're actually doing this here. They're really taking it to extreme. But when you do this part, 1 squared minus this squared, this comes out much easier than what you might guess. This just becomes pi. You could have done that in your head rather than doing all this. So that's just pi. But here you have pi times the interval from 1 to 2 of 2 minus y, which is what I said. Okay. And then when you do this interval here, what is the antiderivative of 2 minus y? 2y minus y over 2, right? Y squared over 2. Yep. Okay. I can't believe we're still doing this. This is pi, and this will be, and if you do this, this will be 4 minus 2, which will be 2, minus 2 minus 1 half. That would be 3 halves. So 2 minus 3 halves is 1 half. So 1 half pi plus pi is 3 halves pi, which is exactly what we got. So it wasn't too bad that way either, but a lot more work and a lot more thinking, a lot more writing. I'm just too lazy for that. So it comes out, oh, yeah. It comes out 3 halves pi. Okay. Yeah. And then this method, the shell method, which sometimes seems a little harder, in this case, just a piece of cake. Okay? Yeah, the p of x is x. The h of x is x squared plus 1. And 2 pi times integral from 0 to 1 of x times, yeah, we did all that. And we got exactly that. And we plugged it in and got that. So much, much easier. Much more straightforward. Any questions? Okay. Whoa. They're acting like that's the end of the section. And that was merely example 3. They're skipping example 4. They're skipping example 5. Okay, so let's go back and do example 4. I think I'll go back to dark color. It's not really black, but it's close to it. The volume of a pontoon. Yes, we want to know the volume of our pontoons. The pontoon is made in the shape shown in the figure. Thank you so much. The pontoon is designed by rotating the graph of y is equal to 1 minus x squared over 16 from minus 4 less than or equal to x less than or equal to 4 about the x-axis. Okay. And x's and y's are both measured in feet. Find the volume of the pontoon. Okay. Now, trying to think of the easiest way to do this. My first inclination would be to write this as 16 minus x squared over 16 and evaluate that from minus 4 to 4. And of course, at minus 4 that would be 0, and at plus 4 it would be 0, and anything in between the two we get up, excuse me, maximum of 1 in the center. So I don't know which is easier to fiddle with. Somehow the top one seems to be me to be a little easier, but they don't. Okay. And revolving that around the x-axis. So since everything is given in terms of x, what you reckon? Yeah, let's do a dx. And what method would that be then? Second? Disk, for sure. Okay. Now, being the lazy person that I am, if you look at the picture in the book, and I'll try to do a cursory representation of that. If this is your 1 minus x squared or x 16 minus whatever if this is that curve from minus 4 to 4, and you're revolving around the x-axis, okay, like I've shown here, and you do your dx here, anything, actually you're only doing the top half of that dx, okay, because you're revolving that. What do you notice about this? One, the volume of this thing. Now, if I had drawn it anywhere close to accurate, you see the volume on this side is the same as the volume on that side. So I was going to do twice the volume from 0 rather than minus 4. I'm just too lazy to do the other. Okay. I like integrating from 0 as a limit. It's so much more fun. So you okay to do that? So what would it be then? The volume of that pontoon would be, I'm going to put the 2 because I'm going to split it. And we're going to go 0 to 4, and we're going to do dx. Everybody agree those are all in place? Okay. What goes next? Anybody?
Radius.
Second?
Radius.
Okay, radius goes in there somewhere. And what's your radius? This is your radius here. And this curve here. Now, I don't know which you prefer. I kind of like this one. 16 minus x squared over 16. Though it looks a little more complicated, I kind of like it better. But that's me. Yeah, and you're going to square that, okay?
Minus. Back to
dx over there.
Second?
Is that square dx?
Yeah, times dx. Yeah, I've already got my dx down there. So what I was listening for was my pi. I never heard that. Pi r squared dx. Okay, so the pi's got to be in there. Now we have a 1 over 16. And it's squared, so this is going to be 2 over 16 squared. I'm not going to figure out what that is. You could probably know what it is, but I don't know. We'll worry about that later because tomorrow is later. Never mind. Okay, so we're going that, which is 16 minus x squared squared. That seems to be it. So let's go on and figure out what is 16 squared. Anyone know? Isn't that 256? Okay. So half of 256 is 128, so it'll be 1 over 128 pi. Okay. 0 to 4. Let's go on and square that. And since we already did it once, 16 squared is 256 minus, what's the next part of that? Anyone remember? 32x squared here. The next is going to be plus x to the 4th. It's twice the product of the 2. The product of the 2 is 16x squared minus 16x squared plus x minus 32x squared. And then the last one squared. And then that's going to be your dx. Okay? So that's 1 over 128. Well, let's just put pi over 128 times. What's going to be the antiderivative of 256? 256x minus 32 times 6. Well, oh, okay, I'm sorry. I'm already substituting. I probably shouldn't yet. That's 32 x squared x cubed over 3, sorry. You were saying that, I think, weren't you? And the next, plus x fifth over 5. Evaluated from 0 to 4. Okay. Pi over 128. See, the disadvantage of using the 1 item is the numbers get big, but hopefully they'll disappear for us in a minute here. So I'm going to back off on myself a little bit. Excuse me, I got to sneeze. Okay. Are y'all awake now? You know, I have to do that every now and then just to make sure everyone's still with us. You know, I'm going to do something a little bizarre here. Rather than 128, I'm going to put 2 to the 5th. Isn't that correct? Okay. And rather than 256, I'm going to put 2 to the 6th. Okay. Minus 32 is 2. Oh, I may have messed this up. Yeah, I did mess it up. 2 to the 7th. That's what I was just thinking. And this is 2 to the 8th. You can't read that, can you? Okay. Okay. 2 to the 7th, 2 to the 8th. 32 is 2 to the 5th, right? Yeah. That looks too much like 25. 2 to the 5th. Now, this gets even worse. 4 is 2 squared, and I'm cubing that. So that will be 2 to the 6th. Wait. My head's not working well. 2 squared cubed is 2 to the 6th, isn't it? Why did I choose to do this? I don't know. Over 3 plus 2 squared to the 5th, I think is 2 to the 10th. I kind of hope so, yeah. All right, over 5. I don't know if this is going to help any or not, but it seems like I can get rid of some things easier. That's going to be pi over 2 to the 7th. Now let's see what we've got here. The least common denominator here is 2 to the 8th. I mean, common factor here is 2 to the 8th times 1 minus, this will be 2 to the 11th. So that's 2 cubed over 3 plus 2 squared over 5. I think I'm doing this right, but I may not be. All right, so this will just be a 2 pi times, and you don't have to do things this stupidly, but I'm doing it. 2 times 1, oh, and this is evaluated. I left off the zeros, so let's see what we've got here. 1 minus 8/3 plus 4/5. I hope that's right. Least common denominator 15. So this will be pi times 2 times 15/15 minus 40/15. I believe that's right. Plus 12/15. I believe that's right too. Okay. No, it isn't. Something's wrong here. I think I messed up with my 2's in there, didn't I? Because this is supposed to come out (64/15), and I don't think I'm anywhere close, am I? Sorry about that. I shouldn't have ever done it that way. I just messed up somewhere in the 2's. I just thought all those big numbers could be simplified, but I think I botched it. Oh, I see where I did botch it. This was supposed to be a 4 here. Okay, that's one place I botched it really badly. So rather than mess with that, anyway, sorry I even messed with that. It came out 64 pi over 15. Sorry about that. I thought I was being clever with that, but I messed up here when I plugged in a 4 there. I forgot to plug in 2 squared here. I think I did it down here. I think I did it everywhere else, but I forgot to put 2 squared here. So this would have been 2 to the 10th. Then we'd have pulled out more 2. Yeah, let's not even go there. Sorry about that. If I had paid attention, I would have gotten it right. But yeah, you have to get a positive volume, by the way. You know, always helps. Negative volumes don't do too well. So I knew I was coming up with that. Now, it says, what if you want to use the shell method with this one? If you have that thought, lie down until it passes and then go on with the rest of your day. Don't even go there. Yeah, that would be really stink. So you see, this method's some problem perfectly set up for it. Other problems like the last one, shell method, fantastically set up for shell method. This was just mathematics there. I messed up with trying to get too fancy with my powers of 2 and completely leaving off one of them. All right. They also leave off example 5, so let's see if we can get that one more reasonably so. All right. Find the volume of the solid formed by revolving the region bounded by the graphs of y is equal to x cubed plus x plus 1. Now, when I see this, guess what d I want to use? Dx for sure. So I'm going to just put this in up here. I really want to use dx's. Okay, when I see this. Y is equal to 1. No problem there. X equal 1. I don't see any problem there either. About the line of x equal 2. This is your revolving around that line. That's your axis of revolution. X equal 2. Okay. Now, again, it's usually a good idea to draw your graph. Okay. Or at least try to. I know we're doing a 1, 2, I'm going to go a 3, 4 here just in case we need it. And going up, I think we only need, I'll just go on and draw them because I have room for them, like that. Okay. Now, let's first draw y is equal to x cubed plus x plus 1. Let's do it at y is equal to, at x equals 0. What do we get? 1. Okay. Let's do it when x is equal to 1. 3. I did need that. Okay. I lucked into that one. Okay. So the curve is doing something like, I don't know what kind of shape it's going to do. I kind of do. It's just going to do something like that. Okay. probably not exactly like that, but the book looks fairly like that. Y is equal to 1, that's that line right here. X equal 1, that's the line right here. Okay, so it's basically this little sort of triangular looking region there going around the axis of x equal 2. So this thing is going over here. Let me see if I can replicate on this side. Here to here. Okay, so this is going this way. Now what did I say I might want to do? dx's. So what kind of method would you suggest that would be then? If we're doing dx's. Second? Shall, for sure. And in fact, they're implying here you really have no choice. Because to do a dy here and do a this method, even though there's nothing wrong with the washers here, they're fine. What's your chance of getting this as a function of y? X as a function of y. 2 chances, slim and none. Okay, it's not going to happen because that is not. Is that an x squared? Yeah, you could probably do it. Okay, x cubed. No way. So you're stuck with this method. I mean shell method, because it's the only possibility here. So there's your dx. Okay, the height here is merely what? What is your height here? Your second? I'm sorry, this is the height. Let me erase what I just did. I don't know what this was. Okay, this is your height. What is it? A little louder.
Function plus 1?
Okay, is the function minus 1? Yeah, okay. It's x cubed plus x plus 1 minus 1. So it's x cubed plus x. You see that? The height of this is the top minus the bottom. And since you're going from y is equal to 1, you're stuck there. So it's this minus that, this minus that. Okay, that's your height. So there's your p. No, that's your h of x. Okay. What else you need since you're doing shell?
Radius.
Radius, and what would be your radius? Not 1.
1 plus x.
Okay. Is it 1 plus x? Or isn't it just x? Okay, oh, wait. Sorry. You probably are right. Okay, your radius, you're revolving around here. So yeah, it's, I gotta get my pen back. There it is. Okay, this value here is x, what I was drawing here. You're going from here to there, so that's 1 minus x. So whoever said that, 1 minus x, that's your radius. Someone said it, right? Didn't I hear someone say that?
Said plus.
Wait. Yeah, I believe it's 1 minus, isn't it? Yeah. It's this length minus that length. Oh, wait. No, you're right. Wait. Okay. It's no, at first it's 2. I'm sorry. It's 2. That's your center of radius here. 2 minus x. Okay. Yeah. So that's going from 2 to 0. Yeah. I mean 2 to 1. I think it's 2 minus x. Do you see why I say that? The length here is from this end to that end. 2 minus x, and this is your x value here, where x is going from 0 to 1, so that would have the length going from 2 to 1, okay? And that is the radius that goes around there. So I believe that's right, okay? 2 minus x. And I think the rest we just write down. So what will it be? The volume will be what? Now, are we already out of time? Awfully close to it? No, wait. No, we go to 2. Got it. Plenty of time. Thought we shouldn't be. Okay. All right. So what will that volume be? 2 pi. Good place to start. Integral from?
So when you're looking at the integral, is it changing the x's?
Yeah. Yeah. If you do dx's, the integral better be x's. So it's going from 0 to 1, right? Okay. I can tell you anything, can I? Okay. 0 to 1. Your radius is 2 minus x. And your height is x cubed plus x dx. Now,
So why is it 0 to 1 and 0 to 2?
okay, you're only integrating from here to here. This is revolved around there. Now, there's a part of me that would rather do this part over here, you know, because that just seems to feel better. But I think it'll do all right doing it this way too. It's going to come up with some weird numbers. But let's see. I may be wrong, and we may find out we have to do it a different way. But I think this will work. Let's try it anyway. What would be the first thing you would do? For that, yeah, multiply it. Okay, so this will be, let me do it somewhere up here. V is equal to 2 pi times the integral from 0 to 1. And what do you get when you multiply those? Let's do your firsts. And what do you get there? 2x cubed. Now we can do the outers if we want to. It really doesn't matter. Plus 2x. And then the innards. Minus x to the fourth. And then your lasts. Minus x squared. I don't think we've got any like terms there. And then that's going to be times dx. So let's see what happens. Your volume is equal to 2 pi times, you do the first one. Second? I'm not hearing well, sir.
Is that first term in x?
Yeah, oh, you're making fun of my writing now. Okay, I got it. It doesn't hurt too much, but, you know, I remember you. Okay, never mind. Go ahead. What do you get? Second? Okay. 2x for the fourth over 4, which becomes?
1/2 x to the third. Yeah.
Is that right?
Yes.
Okay, good. All right. Next. X squared. Next. Okay, got it. Next. X cubed over 3. And now comes our fractions, which is my favorite part of all time. Oh, and this is evaluated from 0 to 1, which will then be 2 pi times, I believe it's 1/2, plus 1, minus 1/5, minus 1/3. Now, here's where things are looking up from the last problem. I'm going to get a positive volume. I feel a lot better. Okay, so last time when I saw a negative volume coming, I knew I was in serious trouble. Okay, least common denominators are is, what would it be? 30. So this will be 15 thirtieths, right? Plus 30 thirtieths minus 6 thirtieths. Wait, is that right? Yeah. Minus 10 thirtieths. I believe that's right, isn't it? I'll do the zero parts. They're all zero. Okay? And that would be 2 pi times, that would be 15 plus 20 would be 35 minus 6 is 29. Is that right?
Yes.
That can't be right. Yeah, can it? No, that's 40. It's 39, isn't it? The old gray cells ain't what they used to be. No, 35 minus 6 is 29. Yeah, 29 thirtieths. So that would be 29 pi over 15, I think. Oh, goodness gracious, they got it right finally this time. Okay. 29 pi 15ths. So, yeah, just trust the integration and the steps to take care of things, and they do. When they do. Okay? And I think this time it did. All right, good deal. That finishes 7.3. Homework exercises here would be, I would say, do either 3 or 5. They give you pictures there, and you do those two. They're both at Calc Chat. Then do any of the odds, 7 through 11. They're all at Calc Chat. 7's at Calc View. Do either 13 or 15 or both. They're both at Calc Chat. And then any of the odds, 17 to 21. They're at Calc Chat with 17 at Calc View. Then do either 23 or 25, both at Calc Chat. 23 is at Calc View. Do 27, it's at Calc Chat and Calc View. 29 and or 31, both at Calc Chat. 33 or 35, they're both at Calc Chat. 37 is exploring concepts, as is 39. They both should be at Calc Chat. 41 should be at Calc Chat. Either 43 or 45, both should be at Calc Chat. And then I would say any of the odds, 47 through 55, or at least 53, they should all be at Calc Chat. 55 is sort of an exploration. If you want to do some exploring, you can try that one. And 57 then is sort of a, I would say 57 and or, let's see, what, I'd say any of the odds 57 through 61. And then there's a section project, which looks pretty interesting, if you're interested in this type of thing. And that would, I don't know if that's a Calc Chat or not, so you can look at that if you're interested. That's not one of the problems. So I'd stop at 61. Any questions? All right. Then let's move on from here. And we've got another about 50 minutes or so. So let's see what happens when we clear this, discard that, and move to this, 7.4. Okay, finding volumes. Areas between curves. That was, what, 7.2? No, 7.1. Then we had 2 ways of finding volumes, disk 7.2 and shell 7.3. Now another application is, there we go, getting lost on what I'm doing here. Application of integration, we're going to do arc length and surfaces of revolution. Okay, areas of the surface of revolution rather than the volume of revolution. And start off though with arc length. Okay. I can't remember. Y'all probably didn't do arc length at all in Cal 1, did you? I don't recall that you do. I'm having trouble keeping you straight. We'll find the arc length of a smooth curve, which is a little more complicated than what it sounds. And by the way, I see some people breaking. Why don't we take, I think we're over halfway through, why don't we take a break? Since Jake's back, it would be a good idea too. Because I bet you there are a few bladders that need to get rid of lunch. So why don't we pause here, vision or not. So our two objectives here, first find the arc length of a smooth curve. Now, at least thinking of that, it doesn't seem like that would be such a difficult thing. Okay. It is a little more complicated than what you might think. And then once we've got an arc length, then we'll find the area of a surface of revolution. Okay, so let's start with arc length. Okay. Definite integrals are used to find the arc lengths of curves and the areas of surface of revolution. Really the hard part of this, to me, is the arc length. After that, surfaces make more sense, of course. In either case, an arc, or a segment of a curve, is approximated by straight line segments whose lengths are given by the familiar distance formula. D is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Of course, where does this come from? Say again? Yes, Pythagorean theorem. That's exactly where it's coming from. Okay? If you think about this, let's just, let me get my pen set up. Yeah, come on, get back here. Okay, here we go. So let's say there's an arc, okay, going from this place to that place, okay? Now, you can approximate that, okay? This will be x1, y1. This is x2, y2, 2, okay? From those 2 points, the good approximation of that, or not a good one, well, an approximation of that would be the straight line between those 2 points. Now, certainly that's going to undershoot the length of the arc by a little bit. We don't know how much. And what would that be? The length of that would be, this is x2 minus x1. This is y2 minus y1, right? This is y1, this is y2, this is x1, this is x2. And the length of this here is the square root of the sum of the squares. Pythagorean theorem, right? Now, not going to be exact, but it's going to be at least an approximation. Always going to be undershooting what the length of the actual arc is. So there's the distance of the straight line segment, that one of those, somehow in there should be a straight line segment. Use your imagination. Okay. The rectifiable curve, boy, what a word that one is one that has a finite arc length. Okay? So if you got some curve that's going to infinity somewhere, it's not going to be rectifiable. Okay, so anything that has a finite arc length, a rectifiable, which I think means you can approximate it by a right triangle. Rectifiable. Okay. I think that's what that means. I don't know. Don't run into that word very often, so I'm making a guess there. Okay, you'll see that a sufficient condition for the graph of a function f to have a rectifiable, to be rectifiable between a, f of a, xy, and b, that's x1, y1, b, f of b, x2, y2, is that f prime be continuous on ab. Okay? So whatever this function is that's describing this thing up here. So, if it were a cusp type thing, hang it up. That's not continuous, first derivative. Maybe a continuous function, but not a continuous first derivative. Or something like the absolute value function or minus absolute value. No, those are not continuous first derivatives. You need something that has a continuous first derivative on A to B. Such a function is continuously differentiable on A to B. Okay, its derivative is continuous. And its graph on the interval A to B is a smooth curve. So therefore, cusps and corners and things like this out of the picture. And certainly, this continuous out of the picture. Okay, so it has to be a nice smooth curve, continuously differentiable. Okay. So let's consider a function y is equal to f of x. It looks like one to me. That is continuously differentiable on the interval a to b. Here we're going a to this b, so just this portion right here. You can approximate the graph of f by n-line segments. The first one you hardly can see. There's the second one. There's the third one. Well, they didn't draw these two. That's why you can't see them. They just drew one of them. Okay. Approximate the graph of f by n line segments whose endpoints are determined by some partition. A is your x of 1 going to x of n, which is your b, and you have so many x's in there. And just do that partition however you do it. They don't have to be even. They don't have to be anything else. So just any partition there. Okay. So for any partition between any 2 points, the delta x is the x2 minus x1, x of n minus 1 minus x of n minus 2, you know, whatever the partition is there. That's your length here. Your y is your y2 minus y1, which is f of x2 minus f of x1. Okay, there's that one. And that then, the distance formula that we just had would be what you use these two things on, okay, to approximate that length there. Okay, now, obviously, like I said before, that's going to undershoot the arc length, because this is the arc length, okay? Y is equal to f of x from A to B. So that's going to approximate it for us. Now, by letting your delta x of I be x of I minus x of I minus 1, delta y of I be y of I minus y sub I minus 1, you can approximate the length of the graph by the s just between those two would be the summation of all your i's going from 1 to n of the difference squared, because that's square root of that. That's your Pythagorean approximation there. Which now, this is your delta x sub I. This is your delta y sub I. So let's just shorten it and do that. Delta x sub I squared plus delta y squared. Square root of those, sum of those squares. Now here's the tricky part. Okay? What we're going to do is under the square root, we're going to, no, over here on this term, there's a reason. A method to the madness here, hang on to it. They're going to multiply the second one by delta x of I squared and divide by delta x of I squared. Okay? Now, I would have done it slightly differently, but this is just as good. Okay? Then we're going to factor out, we got a common term of delta x of I squared there, and we're going to take a square root of it, right? So that'll just be a delta x of I outside of the square root. When you factor it out here, you have a 1. You factor here, you have delta x of I over delta y sub I over delta x of I squared. Okay? Now, let your n go to infinity, meaning your delta x's are going to 0. Okay? They say your norm going to 0, n's going to infinity. So this becomes an integral. This becomes a dy over dx squared, square root of 1 plus y prime squared times dx. There it is. There is our arc length formula. So the s is the limit as this goes to 0 between your n is going to infinity of that and that limit, okay, because, oh goodness, let's do it again and again, because the f prime of x exists for every x in the interval, from x to I minus 1 to x. The mean value theorem guarantees that the existence of some c sub I on that interval such that the okay, this is going back. Remember, this is the difference between your x's here. This is y2 minus y1, and that's your x2 minus x1. Okay, that's going to be the derivative at some point in between there. If your curve's like this, your triangle's like that, someplace the derivative of the curve is going to be exactly the same as the slope of the hypotenuse there. So this will mean someplace there that this will be some derivative of some intermediate point c sub I. Okay. The other way I'd say, it's just, this looks like a derivative, doesn't it? dy dx squared. Okay. And that's exactly what it is. Okay. Now, because f prime is continuous on a to b, it follows that the square root of 1 plus f prime squared is also continuous and therefore integrable. I don't want to say how we're going to integrate the square root over 1 plus something squared, but theoretically it should be integrable on a to b, which then implies that this limit of this, as this is going to 0 and n going to infinity, becomes your integral from a to b of the square root of 1 plus f prime squared dx, where s is the arc length of L between a and b. Strange little formula here, but it works. Now, if you think this is a strange formula, just imagine what kind of contortions the authors have to go through to find the function that when you take its derivative, square that derivative, add it to 1, and then take a square root of that, you've got something that's integral. Okay? In real life, you're going to be doing most of these by finite difference, finite, this is something you're going to do numerically. Because to get a function whose derivative squared, added to 1, take a square root is something that is integrable. Good luck if you just pick any old function f. Okay? Very simple functions f will usually work very well there. Okay? But anyway, expect to see some odd things. So here's the definition of arc length, as if we had just said it, that the function y is equal to f of x represent a smooth curve on the interval a to b. The arc length of f between a and b then is the s is equal to integral between a and b of the square root of 1 plus f prime squared, square root of quantity 1 plus f prime squared dx. Similarly, for a smooth curve, x is equal to g of y. Reversing these, the arc length of g between c and d is integral of this, and this is the derivative of g with respect to y squared and dy. So either one of these orientations will work. Key is finding functions that when you do all these things to it, you get something that's integrable. Okay. So, this one should be a piece of cake, and it is. Find the arc length from x1, y1 to x2, y2 on the graph f is equal to mx plus b. Anyone want to hazard a guess of what that arc length is? Well, what is that the graph of? A straight line. So the arc length is going to be the length of that line. Okay? So this should be pretty easy. But we're going to do it the hard way, right? What do we say we did to do an arc length? What's one of the first things we're going to need to do? Second? Take a derivative. F prime of x is equal to what? Say again?
It is just M.
Just M, you got it, okay? The derivative is the slope of that line, right? I mean, that's what derivative is, okay? What's the next thing we're going to do to that? Remember our formula? What happens to that prime in your formula?
Squared.
You're going to square it. So f prime squared, or f prime of x squared, is going to be what? M squared. All right, got it. Good deal. Okay. What's the next thing you're going to do to it? Add 1. Okay. So 1 plus f prime of x squared is m squared plus 1. Or 1 plus m squared. It doesn't matter. What's the next thing you're going to do to it? Take a square root of it. So I'll just take a square root of this and a square root of that. Okay? This is really looking fun, isn't it? All right. And then this is what we integrate. Okay? So we're going from x1 to x2. Okay? So the arc length is equal to the integral from x1 to x2 of the square root of m squared plus 1 dx. Now, of course, m's a constant, it's a slope, and add 1 to it, it's a constant, and then take a square root of that, and that's a constant. So all this can come outside. So this is equal to the square root of m squared plus 1. And what's the integral from x1 to x2 dx? Antiderivative of dx. X, right? 1 dx, that would just be x. This would be the square root of m squared plus 1 of x evaluated from x1 to x2. Right. Okay? And that would be what would that be? x2 minus x1. Okay. Now, I've been carrying around the m. They wrote the m as x or y2 minus y1 over x2 minus x1. So let's do that, and that would be, so m squared would be what? Squared over x2 minus x1 squared, right? Okay. Now, add 1 to that, and you get y2 minus y1 squared minus or plus x2 minus x1 squared over x2 minus x1 squared. Would you agree with that? What I did was write the 1 is x2 minus x1 over x2 minus x1. So it would be this plus that. These are the denominator of that. Okay? So we need to take a square root of that. Okay? Now this is all what that is. Okay? And if you take the square root of this, that denominator is a perfect square. So this would be the square root of y2 minus y1 squared plus x2 minus x1 squared over x2 minus x1, because you take the square root. That cancels that. And basically, that's your length, okay? The length of the line between those 2 points, which is exactly what the arc length is. It's the length of the line between those 2 points, okay? Did that feel like a waste of time? I mean, no, don't answer that question, okay? Yeah, you just get exactly what you expect is the length of the line, okay? That's what it is, the length of the line. And that's all they wanted you to get. By the way, and I meant to say this earlier, it was somewhere back here, and I sort of, no, it may have been my last class. Wait a minute. Yeah, I'm sorry. Forget it. Here we have, at the top of the page, a really incredible-looking guy, Christian Huygens, a Dutch mathematician, invented the pendulum clock, okay? And he and James Gregory, Scottish mathematician, both made early contributions to finding the length of a rectifiable curve. And so there's 2 different names of people you might choose if you are still looking for a paper topic. How did they go about doing it, or just who they were, whatever. You can see several potential paper topics there. There was one in my last class I forgot to mention, but anyway, I'll mention that again next week or later on Wednesday. All right, so let's move on. Let's see it. Let's watch them and see how they do it. We'll erase all that, see what they do, because f prime of x is simply m, but m, they start off with y2 minus y1 over x2 minus x1. That is the slope of any straight line, okay? Then they go about doing their formula. S is equal to the integral from x1 to x2 of the square root of 1 plus f prime squared. So that is going to be this thing squared, okay? And you basically do how we went about deriving this, you do it in reverse. It's basically what it looks like. So that's the integral from x2 minus x1 of 1 minus all that thing, square root of 1 minus all that thing, 1 plus that squared, dx. When you square that, this is sort of reverse of what I was doing. You put this over, express the 1 as x2 minus x1 squared over x2 minus x1 squared, and then you have x2 minus x1 squared, y2 minus y1 squared as your numerator, over this as your denominator. And this is all a constant, so that's out front, and the antiderivative of the dx is x. So that's why that's in there. And then that's what you evaluate this. This could all come out front. I don't like the way they wrote it, but it is correct. So you evaluate x between x1 and x1. This is under the square root, so you can take the square root of the denominator, and then that goes out, and that leaves you with just the square root of the numerator, which is what they got, the length of the line. Yay, okay. We saw that to begin with, which is the formula for the distance between the 2 points in the plane, and that's exactly what your arc length of a straight line is, the length of the line, okay? The formula for the arc length of a graph is the same as a standard distance formula. Big surprise, okay. Now, that we've got the arc length down, they're moving to finding the area of a surface for revolution. But, as promised, they did the very simplest one. They skipped example 2, example 3, example 4, and example 5. Shame on them, okay? These are the ones that really take some effort. So let's do example 2 here. They did the very easiest one. So find the arc length of the graph of y is equal to x cubed over 6 plus 1 over 2x on the interval 1/2 to 2, okay, as shown in the figure. Now, I guess I could draw the figure, but I don't see any real point to it here. But just for those who don't have books, this weird-looking little formula here, this would be this portion. It looks a little bit like a Watt-sided parabola, and that's as good a description as any, but it's not a parabola, but it's an odd-looking little curve like that. Looks pretty simple in nature until you look at this thing, and like I said, to come up with functions that you can actually do this, you come up with some weird-looking functions. And this, to me, is a fairly weird-looking function. Now, what's one thing you're going to do to that y? Okay. Before I would do that, I would rewrite it somewhat slightly. How would you rewrite it? Or would you? You may not. I think, frankly, I'd do 1/6 x cubed plus, what did you say?
2x to the negative 1.
How about 1/2 x to the minus 1? Is that okay? Okay, the other would work too. What you said was exactly correct. I think this is maybe just a little easier to do. Okay? Now take a derivative. Y prime is equal to
X to the 4th over 24.
no, you're taking a derivative, not integrating. Okay?
X squared over 2.
Say again?
X squared over 2.
Okay, not quite.
Divide 3x squared.
3x squared over 6, which is 1/2 x squared. Okay, finally got it out of you. Next. Sending you back to Cal 1. Okay. Negative 1/2 x to the negative 2. Ah, weird, huh? And what's the next thing you're going to do to that after you take a derivative? Square it. All right, let's square it. I can't wait. Okay. All right. So y prime squared is going to be, how do you do that? Okay, I heard a 1/4 x to the 4th. Is that what I heard? All right, good first term. Okay, yeah. Well, yeah, minus.
1/4.
Okay, only it's twice that, so it's. Oh, y'all do you do it at one time, or you going to do 2 steps or multiple steps?
Oh, I was thinking of just squaring the front.
Yeah.
stuff.
Okay. What? I don't know. You may be doing it right. What I was going to do was square the first term, which we did. Twice the product of the 2 terms. Is that what you were doing?
I was doing the.
Or you were doing foiling it?
Yeah.
Okay, yeah. Well, let's do it your way. Okay. So what would be the next? Minus 1/4 x to the what? Nope. You add the exponents. It's x to the 0, which is minus 1/4. Okay. I'm still a little, wait, I don't know what I just did there. Eraser is what I wanted to do. Okay. Now, time out, I've got to think now. You're foiling it basically, right? 1/2 x squared minus 1/2 x to the minus 2 times 1/2 x squared minus 1/2 x to the minus 2. That's what you were doing, right? You did this one first. No. You did first. I don't even know how to spell FOIL anymore. Oops. I don't know how to erase either. Okay. All right. You did the first, okay, and that was 1/4 x to the 4th. And now you're doing this one. Is that right?
First,
Second? Yeah. And then this one would be? Yeah, another negative 1/4. And then finally the last one would be? X to the minus 4th. Perfect. Okay, and then when you combine like terms, what do you get? 1/4 x to the 4th minus 1/2 plus 1/4 x to the minus 4. Perfect. Okay, I'll put brackets on one side, squares on the other. Or the way, a little bit of a shorthand, square the first, twice the product of the two. The product of the two is 1/4, just minus 1/4, twice that is minus 1/2, and then the next one squared. Okay. And then you do what? Add 1 to it. So I'm going to remove the parentheses here and just add 1. Okay, so this will be y prime squared plus 1, so I'm just going to add 1 to that. Sound okay? Okay, and what does that give us? Now it just becomes a plus 1/2 plus 1/4 x to the minus 4. Agreed? Because you're adding 2/2 to this, and the only term without x in it is these two, and that would be 2/2 minus 1/2 is plus 1/2, right? All right, good. And then what do we want to do? Second? Square root of it. Yeah, we're going to take the square root of everything here. And here's where the magic comes into play. That happens to be a perfect square. Anyone know what the perfect square is? It's not one you would see every day. But if you think back, when you squared this, you got a minus 1/2 here. If that had been a plus here, you would have gotten a plus 1/2 there. So it's the perfect square of this thing with a plus. It's magic. I told you that. It's magic that happens to be the case. Because the only difference between this and that, this is what we got before we added this. That was the perfect square of this. And this is the perfect square if you had a plus there. It looks like a shell game, but it is indeed true. So this is, the square root of that is 1/2 x squared plus 1/2 x to the minus 2. That's what the square root of that is. And y'all don't believe me, do you? I see all these impossible like looks on your faces, but it is. Try it. Go back and square that thing and see if you don't get the very thing right there. You do. I promise. Okay. So, there we have taken the square root of that thing, and this is what we integrate. Okay, so your arc length is going to be the integral from 1/2 to 2. Remember, that's this is the interval on x of the square root of these things here, which comes out to just be 1/2 x squared plus 1/2 x to the minus 2 dx. Okay. All right. Now, if it's okay, I'm going to erase some stuff so we can go and do the integral. Is that going to be okay with you?
Yes.
Okay, so I'm going to erase everything that's below that. because we've already done it and used it and dealt with it. And don't you dare come back and say, okay, how did you get from here to here now? No, it's all gone. So speak now or forever hold your peace. It's already too late, so hold your peace. Okay. I've often wondered what this looks like at home. It has to be weird. Just all of a sudden things start disappearing. And it's weird little. Okay. So now we need to integrate that. And what will it be? X cubed over what? 6, perfect, plus, minus, I think, won't it be? Take your time, do it. What do you get? Say that again. X to the minus 1 over 2. I believe she's right, isn't she? Because if you take the derivative of this, you get 3 times this would be x squared over 2, yes. And you take the root of this, you get plus x to the minus 2. So that's right. And we'll evaluate that from 2 of my favorite things, from 1/2 to 2. I really like that. And what would that be? Oh, boys. Powers of 2 again. What's this? 8 over 6 minus. Okay, say that one more time. 1/4. Perfect. Okay. That's the upper one. Now the lower one would be okay, minus or what you say? 1 over. I couldn't hear.
You'll have 1/8 over 6.
1/8 times 1/6, which is 1/48. Is that right?
Yes.
Okay. And then minus a minus, which would be a plus.
1. No.
I think you're right.
Yeah.
It's 2 over 2 is 1. Okay. Isn't this fun? All right. Don't know if we really want to reduce the 8/6 because least common denominator is 48, isn't it? Will 6 go into 48? Yeah. Okay. So that'll be 48. And that would be 64, right? Minus 12, right? Minus 1 plus 48. Okay. And that would be 112, I think around 99 over 48, which I think will reduce to be 33 over 16. Is that right? It's going awfully fast. Let's see what we got. 33/16. My goodness, I got it right in the book too. Okay. Any question? Was it that fun? Now, like I said, to get a function that you'll do all that with, that you guarantee you can actually integrate, you come up with some weird functions, and that was weird enough. X cubed over 6 plus 1 over 2x. Who would have ever thought that would have come out very nicely? But it does. Weird number, but you know, at least it's integrable. All right. Any questions on that? How are we doing on time? We've got maybe 10 minutes, or that much. It's 2:30, 2:25, yeah. So about 10 minutes? Okay. I don't know if we'll get the next one done. I kind of doubt it. But let's see. All right. Find the arc length. Let's try it. Let's see. That last one took us well more than 10 minutes, didn't it? It felt like it. Anyway, I don't know if it did or not, did it? Okay. I have a feeling this will be, if anything, maybe a little longer. So why don't we hold and pick up this one next time? And I don't believe, I think I forgot to bring up my eraser. So let me see if I can erase with this. And sorry, I'm going to cheat you out of a few minutes of your tuition dollar here. Forgive me. Write me up, whatever. Okay. We'll begin next time with example 3 on page 476. Okay, homework exercises in this one. Do number 5. It should be at Calc Chat and at Calc Chat. Then do any of the odds. Do either 7 or 9. They should both be at Calc Chat. 7 should be at Calc View. Then do any of the other odds, 11 through 19. Try doing any of the odds 21 through 29. Some of those may be a little more wacko, but give them your best shot. Try doing 31. Okay? And I think that the next one, 33, is going to be very similar to example 5, which we haven't done yet. So we'll hold off of that one until then. Okay? I sort of hate to rob you out of this many minutes of your tuition dollars, but I really don't think we'd have a chance to finish example 3, and then I wouldn't have had a chance to do that. So, sorry, don't have to let you go early today. But guess what? There is no refund. Okay? Even though I cheated you out of this, you got to stick with it. Okay? Good deal. We'll pick up again on Wednesday with example 3. I hate doing that, but there's no way we were going to finish that next one in 10 minutes.
Yeah, we only had like 2 minutes.
Huh?
I think we only had like 7 minutes left.
7 minutes, okay. What a shame. Okay. I feel like such a cheat.